Hello and welcome to the Further Maths Support Programme revision recordings for A-level modules. Today we're going to be looking at Edexcel Mechanics 2 and we're going to be looking at the fifth and last part of Edexcel Mechanics 2 today. We're going to be working on the impact topic, collisions. You can see here that there are 5 recordings for Edexcel M2 altogether. If you wish to revise any of the other topics that are listed here, then you can find those on the same site that you found this recording. So here's an excerpt from the Edexcel specification for collision. Students need to know about momentum as a vector and the idea of the impulse momentum principle in vector form, along with conservation of linear momentum. You need to be clear on direct impact of elastic particles, including Newton's law of restitution, and the idea of the loss of energy due to an impact. You will also be expected to know that the coefficient of restitution, E, takes values between 0 and 1 inclusive, where 0 involves coalescence of the particles that are impacting and 1 involves perfect elasticity, so no loss of energy. You'll also need to be able to deal with impacts of successive varieties, so one particle bumping into another and then bumping into a third and so on. Collision with a plane surface will also be needed, but there's no oblique impact in this section. That's in a different module. Okay, so ideas. A diagram is crucial in these ones, putting all the information onto the diagram, and particularly taking care with directions. You need to have the idea of conservation of momentum for the whole system during a collision. And the idea that impulses change in momentum for a single body. Notice that if momentum is conserved for the whole system, but momentum is not conserved for individual objects in a system, only in the whole system together. Do take very great care with directions when you're dealing with impulse and momentum. And for this reason, vectors are very useful in dealing with collision questions because they do the hard work on direction for you. This section here is Newton's law of restitution. Separation speed is E times approach speed. And here there's just a little reminder of how to think about conservation of momentum and Newton's law of restitution calculations. So let's just take a look at this. In this first case, both particles are moving left to right before the impact, and both particles are moving left to right after the impact. So the momenta for all of these particle situations are positive. They're all going in that same positive direction. So the momentum beforehand would be MAUA plus MBUB, and afterwards MAVA plus MBVB. Newton's law of restitution, however, looks at the separation and approach speed. So in this case, because VB is away from A, it's contributing to the speed they're moving apart, so it's positive. However, A is moving towards B, so it's reducing the speed with which they're moving apart, hence it's negative in the relative speed of separation. Similarly on this side, because B is moving away from A initially, the speed of B is reducing their overall approach speed, their relative speed towards each other. If we start with them moving together and finish with them moving apart, then the momenta have differences in, because the velocity of B initially is in the negative direction and the velocity of A afterwards is in the negative direction. But Newton's law of restitution will be all sums, because the total relative velocity is increased by both UA and UB when they're moving together, and the relative velocity apart is increased by both VA and VB when they're moving away from each other. Just a quick check that's worth looking at. In these questions you're often expected to show the momentum calculation and the Newton's law of restitution calculation, and you will always find, by the structure of these, you will always find that these calculations contain one sum and one difference. If the momentum calculation is all sums, all positives, then the Newton's law of restitution calculation will have negative in it, like this. It's just a little sort of shorthand check to make sure that you're doing it right. Okay, so let's take a look at an example. If you're playing along at home, please take the chance here to pause the recording and work through on your own if you choose to. Okay, so initially here we're looking for the magnitude of the impulse of the bat on the ball. So the ball has a mass an initial velocity and a final velocity. So we're going to use impulse equals change in momentum. We're going to do that in vector form. So I'm going to use the formula J, that's impulse, is mass times the difference between the final velocity and the initial velocity. So impulse equals change in momentum, mv minus mu, and I've just factorised that to simplify it down a little bit. So the impulse that we're looking for here, actually I'm just going to make that an equal sign, is going to be 0.5 times final velocity, which is 20I, minus initial velocity, which is 10I plus 24j, subtracting both of those from the initial velocity. That's going to give me, if I work that through, that's going to give me 5I minus 12j. Just be cautious there. The final mark in this bit is for finding the magnitude of the impulse. Don't forget to do that. So the magnitude of the impulse here is going to be the magnitude of that vector, which is 13 Newton seconds. Impulse measured in Newton seconds. Okay, for part B, the size of the angle between vector I and the impulse exerted. Well, our impulse is 5I minus 12j. Let's just do a little sketch of that. 5 across and 12 down. So if I say that alpha is the angle I'm looking for here, this direction here is the I direction. So the angle we're looking for there, tan alpha, is going to be 12 over 5. And again, if we pop that into a calculator, we should find that alpha, I think, is 67.4 degrees, just given to one decimal place. And finally, the kinetic energy lost by the ball in the impact. So this is going to be initial kinetic energy, let's call it half mu squared, minus final kinetic energy, let's call that half mv squared. And we can use our vector magnitudes here, so that's going to be a half m. I'm just going to factorise here. 0.5 is the mass, and then u squared, that's going to be the initial velocity, that's going to be 10 squared plus 24 squared. And from that we're going to subtract the square of the final velocity, which is going to be 20 squared. And if we work that through, I think that gives an exact value of 69 joules. Because it's energy, it's measured in joules. Okay, here's a second example. Again, if you want to pause at this point and work through the question yourself, that would be fine. We've got our particle P that's got mass m, and it's moving at 6 meters per second, and it bumps into a wall. There's my wall, sorry it's not very straight, and it rebounds from that wall in the opposite direction, and I'm going to say that it comes out with velocity v, and you're told that the kinetic energy lost in the impact is 64 joules, and you know that E is a third. Okay, so using Newton's law of restitution, we know that separation speed is E times approach speed, so v equals a third of 6, which is 2 meters per second. That means that the kinetic energy is 64, and all we're missing from the kinetic energy calculation now is the mass. So let's just put in that kinetic energy calculation. That's going to be, the loss in kinetic energy is half mu squared minus half mv squared, just as it was in the previous question. And we know that that's going to be half m times 36 minus half m times 4, and we know that that's equal to 64 from the question. A little rearrangement on that, I think, gives you m, or I think gives you 32m is 128, and you can divide through by that to show that m is indeed 4. On then to the next part of the question. We've then got P rebounds from the wall and collides with particle Q. So let's just sketch that in. Here's P coming off the wall with velocity 2, and Q is coming towards it with speed 3 here, and it's got mass 2. Oh, sorry, we know m here is 4 now from the previous part of the question. So we need to show that there's going to be a second collision between P and the wall. In order to show that, we've got to show that P has his direction reversed. So just a quick summary here shows that P's momentum right to left is 8, but Q's is only 6 left to right. So I'm going to take right to left as the positive direction for momentum. I'm going to assume that P has its direction reversed, so let's call this VP in that direction. And I'm going to assume that Q also has its direction reversed in that impact. It may or may not do, it's not really relevant whether it does, but that's what I'm going to assume for the time being. I can then apply conservation of momentum. And as I say, I'm using right to left as the positive direction here. So for P, the momentum is 2 times 4, which is 8. For Q, it's 2 times minus 3, which is minus 6. Remember, because Q is moving in the negative direction in terms of momentum. After the impact, Q is now moving in the positive direction, so 2VQ, and P is moving, we think, in the negative direction, so 4VP. We can simplify that down a little bit. 8 minus 6 is 2, and then we can divide through by 2. That gives me 1 equals VQ minus 2VP. I'm just going to call that equation 1. If I then use Newton's law of restitution, separation speed equals E times approach speed. So the approach speed is 5, 3 plus 2, times E, which we know is a third from the question. So that's E times U, that's E times approach speed, is separation speed becomes VP plus VQ. That gives us our second equation. And we can solve those two. If I do equation 2 minus equation 1, that's going to eliminate the VQs. So let's just work that through. VQ minus VQ is 0. VP minus 2VP gives me 3VP equals, and then we've got 5 over 3 minus 1. So VP is 2/3 divided by 3, so 2/9. This is greater than 0, and we can infer from that that the direction of P is reversed, hence it will strike the wall again. And you do need to make sure you put that conclusion in at the end of the question there, because there is always a final mark in the last part of that question just for that conclusion. You know, you've shown that V is 2/9, but what does that mean? You do need to put a little bit of an explanation in about what the actual result of that is. Okay, thank you for watching. I hope you found this useful. I would also strongly suggest that at some point you go and check out the Further Maths Support Programme home website. On this site there's lots of ideas about how the FMSP can support schools and colleges with running further maths, and also support students and provide enrichment and training, etc. for them. I hope you find that useful, and thank you for watching.